Hello everyone. Hope you all watched lecture 3. In the last 3 lectures, we looked at conformations of acyclic compounds. From this lecture onwards, I am going to discuss conformational analysis of cyclic compounds. Okay. Let's start with the cycloalkanes first. So we are going to discuss conformational analysis of cyclic compounds. Okay, let's start with the cycloalkanes. The general formula of cycloalkanes is CH2N, where this N can take values 3, 4, 5, etc. When N is 3, we get cyclopropane. If N is 4, we get cyclobutane. Like this, we have cyclopentane, cyclohexane, cycloheptane, etc. Unlike acyclic compounds, cyclic compounds involve an additional strain called angle strain. Okay. In order to understand angle strain, we have to discuss an important theory called Bayes strain theory. Okay, so we'll discuss Bayes strain theory now. What are some important assumptions of Bayes strain theory? In Bayes strain theory, molecules are assumed to be planar. Okay, so cyclopropane, cyclobutane, cyclopentane, all the molecules are assumed to be planar. Then stability of the molecule is inversely proportional to the angle strain of the ring. If angle strain increases, stability of the molecule will decrease. Okay. Then what is angle strain? Angle strain is nothing but half into bond angle corresponds to the hybridization of the carbon minus the actual angle present in the molecule. Okay. Yeah, here this is very important. First, we must know what is the internal angle in cyclopropane, internal angle in cyclobutane, cyclopentane, cyclohexane, etc. Okay. How to find the values? Right, it's very simple, because we are going to take regular polygons, right? Cyclopropane, cyclobutane, cyclopentane, cyclohexane, right? We are going to take only regular polygons. Sum of internal angles of regular polygon, okay, I will take this sum as S, is equal to N minus 2 into 180 degree. What is N here? N is nothing but number of sides. Cyclopropane has 3 sides, cyclobutane has 4 sides, like that. Okay. So sum of internal angles, total, right? So if you take cyclopropane, in cyclopropane N is 3, so 3 minus 2 is 1, so you will get the total angle is 180 degree. If total angle is 180 degree, then what is the angle, right, at one particular carbon? Okay, so internal bond angle is equal to total angle by number of carbon in the ring. So in cyclopropane we have 3 carbon atoms in the ring, so 180 by 3 is 60 degree. So the internal bond angle in cyclopropane is 60 degree. Similarly, if you go to cyclobutane, in cyclobutane number of sides is 4, 4 minus 2 is 2, so 2 into 180, right, you will get 360 degree. Internal bond angle is 360 by number of carbon in the ring. In cyclobutane we have 4 carbon, okay, cyclobutane we have 4 carbon, therefore 360 by 4 will give you 90 degree. So the internal bond angle, right, at each carbon is 90 degree in the case of cyclobutane. Listen, assuming the rings are planar and all the rings must be regular polygon. Okay. Under this assumption, we can calculate the internal bond angle using this formula. Similarly, if you go to cyclopentane, suppose if I assume cyclopentane as a regular polygon, right, the regular polygon, it has 5 sides, therefore 5 minus 2 is 3, 3 into 180 degree, right, 3 into 180 by number of carbon in the ring 5. So 3 into 180 by 5 will give you 108 degree. So in cyclopentane, the internal bond angle is 108 degrees. Are you able to follow? Right, like this, we can calculate the internal angle in cyclohexane, cycloheptane. Okay, but here keep this in mind. Here the assumption is we are assuming the ring is planar ring and the polygon should be a regular polygon. Okay, yeah, because we also have irregular polygons, so that's why I am stressing this point here. Okay, then, so in the case of cyclopropane, the internal bond angle is 60 degree. So what is the angle strain? Angle strain is half into angle corresponds to the hybridization. See here, all the bonds are single bond, right? See, suppose if you take this carbon has 4 sigma bonds, right? 4 sigma bonds. Okay, so number of sigma bond is 4, therefore hybridization is sp3, right? Hybridization is sp3 hybridization. sp3 means the normal bond angle should be 109.5 degree. This is sp3 hybrid angle, right? If a carbon has sp3 hybridization, then the expected bond angle should be 109.5 degree. But now the internal bond angle in the cyclopropane is only 60 degree. So 109.5 minus 60 will give you 49.5. 49.5 divided by 2 will give you 24.75. This is why we are dividing by 2, because in the ring each carbon participate with the 2 bonds. Okay, so with respect to one bond, what is the strain? So you have to divide the value by 2, you will get 24.75 degree. So this is, listen, this much deviation is there from normal bond angle of 109.5 degree. As the deviation is more, angle strain also more. As angle strain increases, stability decreases. Therefore, listen, cyclopropane has 24.75 degree angle strain, which makes this molecule highly unstable. Okay, yeah. So stability of the molecule is very, very less. Then the next molecule is cyclobutane. In cyclobutane, the angle strain is half into, here also the hybridization is sp3. So the tetrahedral angle, normal tetrahedral angle is 109.5 degree minus the internal bond angle is 90. So 109.5 minus 90 will give you 19.5, divided by 2 will give you 9.75. Now in cyclobutane, the deviation is only 9.75. So angle strain is just 9.75. If you compare cyclopropane and cyclobutane, right, angle strain in cyclobutane is less. If angle strain is less, stability is more. So compared to cyclopropane, cyclobutane is more stable according to Bayer strain theory. Then cyclopentane, if you go to cyclopentane, if you compare the angle strain, or if you calculate the angle strain of cyclopentane, formula 1 by 2, here also the carbon is sp3 carbon. So 109.5 degree is the normal sp3 angle minus the internal angle, actual internal angle is 108. So 109.5 minus 108 is divided by 2 will give 0.75. So 0.75 is the deviation or angle strain. Now see this, angle strain in cyclopentane is less than angle strain in cyclobutane. So cyclopentane is more stable than cyclobutane. Then the next molecule is cyclohexane. In cyclohexane, the internal bond angle is 120 degree. So angle strain is 1 by 2 into 109.5 minus 120. So you will get, if you subtract this and divide the value by 2, you will get minus 5.25. Listen, this minus sign and plus sign, okay, that doesn't matter here. Okay, the deviation, right? The deviation may be positive deviation or maybe negative deviation. Both will give you strain in the molecule, right? So you consider only the magnitude. Listen, here the magnitude is 5.25, angle strain magnitude is 5.25, here 0.75. Listen, so if you compare cyclopentane and cyclohexane, in cyclopentane angle strain is less. So compared to cyclohexane, cyclopentane is more stable according to Bayer strain theory. Are you clear? So what is the stability order? See, the stability order of cycloalkanes according to Bayer strain theory, very important. According to Bayer strain theory, the stability order is cyclopentane is more stable over cyclohexane, then cyclobutane, then cyclopropane. This is the order. Okay. But what is the experimental order? Remember, using thermochemical data, we can calculate the stability of the cycloalkanes. It was found that for here just for understanding purpose I plotted this. So I plotted stability in y-axis and number. See, this is just a rough picture. Okay. Stability, just for understanding purpose I am giving this plot. So I plotted stability in y-axis and number of carbon in the ring in x-axis. So in cyclopropane, right, cyclopropane has less stability. Stability is very low. Then cyclobutane has little higher stability. Cyclopentane, yes, little higher stability. Cyclohexane has highest stability. See, this is very important. According to Bayer strain theory, cyclopentane is more stable, whereas the experimental order shows that cyclohexane is more stable over cyclopentane. Then cycloheptane. Cycloheptane is less stable compared to cyclohexane. Then cyclooctane is less stable compared to cycloheptane. Okay, so this is the order. Okay, I have given some comparative picture just for understanding purpose. So among cycloalkanes, cyclohexane is the most stable one. Cyclohexane, right, is the most stable one. Are you able to follow? Then I like to give one additional information here. As the strain increases, stability of the molecule decreases. Then another one is, if the ring is smaller ring, okay, then flexibility of the ring will decrease. So cyclopropane ring is not flexible, whereas cyclobutane, cyclopentane, cyclohexane rings, they have some flexibility, right, in ring system. This flexibility in the ring, right, makes the molecule to undergo ring flipping. Okay, so cyclopropane does not exhibit conformational isomerism because the ring is highly rigid, so it does not show any conformational isomerism. Whereas cyclobutane, cyclopentane, cyclohexane, right, if you move from cyclobutane to cyclopentane, cyclopentane to cyclohexane, flexibility of the ring increases. Therefore, these molecules, right, cyclobutane, cyclopentane, cyclohexane, these molecules show conformational isomerism. Okay, yeah. Then, so cyclopropane is planar molecule and it is highly rigid. It does not show conformational isomerism. It does not show conformational isomerism. Then cyclobutane, yeah, experimentally it was found that the ring is not planar. The ring exists in the puckered form, right? Puckered ring form. Non-planar ring is called puckered ring. What is puckered ring? Non-planar ring is called puckered ring. And now this puckered ring, right, it's something look like a butterfly, so it can undergo butterfly inversion like this. Sorry. Yeah, see, this molecule shows this type of butterfly motion. Okay, yeah. Similarly, cyclopentane also exists in puckered ring form. It is also flexible, and this shape is called open envelope shape. Okay, cyclopentane exists in open envelope shape. Cyclohexane also exists in puckered ring form. It is also flexible, and it exists in chair conformation, boat conformation. We are going to see different conformations a little later. Okay. Then, okay, let's start with the molecule cyclobutane. If cyclobutane exists in planar structure, the point group of planar structure is T4H. in planar structure, the hydrogen which are above the plane, okay, exists in the eclipsed form. Similarly, the hydrogens which are present below the plane also exist in the eclipsed form. So between the adjacent CH bonds we have eclipsed strain, right? So above the plane we have 4 eclipsed interaction of hydrogen, and below the plane we have 4 eclipsed interaction of hydrogen. So altogether there are 8 eclipsed interaction. So it will be roughly 8 kilocalorie per mole of this interaction will give 8 kilocalorie per mole of potential energy to the molecule. Okay, so you have torsional strain. This is called torsional strain, eclipse strain. Apart from this eclipse strain, torsional strain, we also have angle strain in the molecule. Okay, so this planar structure has torsional strain as well as angle strain. Suppose if the cyclobutane molecule assumes a Puckett ring structure, right? In Puckett ring structure, what happens? Now the molecule is not planar, therefore torsional strain decreases in larger extent. But as the molecule takes the non-planar form, the bond angle here, see here the bond angle, right? Bond angle decreases. So you will get an angle strain, right? So angle strain increases slightly, right? But if you compare the decrease in torsional strain and the increase in angle strain, the decrease in torsional strain is very high. Therefore, the stability of the Puckett ring form, right, is more compared to the planar structure. So cyclobutane exists in the Puckett ring form, also called butterfly form, butterfly shape. Okay. Yeah. So this butterfly form of cyclobutane undergoes ring flipping. Because of the ring flipping, the axial hydrogen, right, in one conformation becomes the equatorial hydrogen, and the equatorial hydrogen, right, in one conformation becomes the axial hydrogen. Okay, so this is actually called, these two are same molecule, right? So they are this type of isomerism is called topomerism, right? We'll discuss this diastereomeric topomerization later. Before that, we'll discuss some more aspects. Okay, so in cyclobutane, see, we have 4 axial hydrogens and 4 equatorial hydrogen. So this is axial, right, and this is axial, this and this are axial, and remaining are equatorial hydrogens. Okay, so remember, in cyclobutane there are 4 axial hydrogens, right, and the equatorial hydrogens exist in the molecule. Okay, then suppose if an R group is substituted, right, in any one of the carbon, right, now what will happen? If this R group is present in axial position, then between this R and the hydrogen atom present at carbon number 3, so if I take this is carbon number 1, this is carbon number 2, right, and this is carbon number 3, between the axial bond of carbon 1 and the axial bond of hydrogen, there will be a steric interaction. This steric interaction is also called 1,3 axial interaction, right? This axial interaction, right, provides some potential energy to the molecule. It raises the potential energy of the molecule, therefore stability decreases. So when R group or any substituent present in axial position, right, then the stability of that particular conformation will decrease. Suppose if R group is present in equatorial position, no axial interactions are there, therefore equatorial position, right, if any group occupy equatorial position, that conformation is more stable over the axial position. Are you able to follow? This is very, very important. So why the axial substituents are less stable, because when substituent is present in axial position, there will be 1,3 axial interactions exist. This axial interaction destabilizes the conformation. Are you clear? Then what is meant by butane-Gauche interaction? We have already looked at this. We have already discussed this in acyclic molecules. Suppose if you have 4 carbon atoms, this is carbon 1, carbon 2, carbon 3 and carbon 4. Okay. If the dihedral angle between this bond and this bond, if it is 60 degree, we call that conformation as Gauche conformation. Since we have 4 carbon atoms, it is called butane-Gauche conformation. In butane-Gauche conformation, there will be a steric interaction or torsional strain. I'm sorry, not steric interaction, torsional strain between the 2 carbon. This torsional strain will give you some potential energy to the molecule. It will raise the potential energy of the molecule by 0.9 kilocalorie per mole. So, one butane-Gauche interaction provides 0.9 kilocalorie per mole of energy, right, to the molecule. Okay, then. Yeah, now we'll discuss some more informations on cyclobutane. In disubstituted cyclobutane, okay, you can put the substituents in 1, 2 position or in 1 and 3 positions. Okay, what is meant by that? See, in cyclobutane, this is position 1, this is position 2, this is position number 3, right, and this is position number 4. So you can put the substituent in 1 and 2 position or in 1 and 3 position. 1 and 4, 1 and 2 are equivalent, so you need not worry about that. Okay. So you can put the substituent in 1, 2 position or in 1, 3 position. Okay. In 1, 2 position, when we'll get cis isomer, when we'll get trans isomer. Okay. If you put one substituent in axial and the other substituent in equatorial, you will get cis isomer. Okay. So what is cis isomer? See, I'll show you here. What is cis isomer? See. Okay, this is cyclobutane. Suppose I'll put one substituent in axial position. Okay, see here I'll put one substituent, say some group R, which is present in axial position, and in the second carbon I'll put this another substituent in equatorial manner. Okay, right. So this is second R in equatorial position, and this will give you the cis isomer. In trans isomer, either both should be equatorial or both should be axial. Right? What is meant by that? See, in trans isomer, I'll draw cyclobutane like this. Now in carbon number 1, we have a substituent in axial position, carbon number 1. In carbon number 2, we have another substituent in axial position. Now, see, by appearance it is very clear that the two R groups are exactly opposite to each other. So it is a trans isomer. So when two R group present in axial position, both axial or both equatorial, you will get trans isomer. One group axial, the other group equatorial will give cis isomer. Similarly, in 1,3 disubstituted cyclobutane, both equatorial and both axial will give cis isomer. One group axial, another group equatorial will give trans isomer. Okay. See, this really requires some practice. So you try to write the cis and trans isomers in notebook, and visually, you observe in your own whether it is cis isomer or not. Okay. How to distinguish cis isomer from trans isomer now. Then comparison of stability. Suppose I'll take 1,2 dimethyl cyclobutane. In 1,2 dimethyl cyclobutane, we will get a cis isomer. So when we will get cis isomer, one group should be axial, the other group should be equatorial. So here I placed one methyl group in axial, the second methyl group is in equatorial, right? Now listen, if you substitute like this, then this conformation involves two butane-Gauche interactions, right? What are the two butane-Gauche interactions? See, this carbon 1, methyl carbon 1, this is 2, this carbon 3 and this carbon 4. This is one butane-Gauche interaction. Then second one, 1, 2, right? Carbon 1, carbon 2, carbon 3, right? And let us take this carbon as 5. So 1, 2, 3, 4 will give one butane-Gauche interaction. 1, 2, 3, 5 will give another butane-Gauche interaction. So the cis isomer has two butane-Gauche interactions. Moreover, this methyl group is an axial, and here we have an axial hydrogen. Okay, so methyl group is, if methyl group is attached to carbon 1, then this should be carbon 3. So there will be 1, 3 axial interaction also exist, which these two, see, axial interaction as well as two butane-Gauche interactions. These interactions raise the potential energy of the molecule in a larger extent. Therefore, cis isomer is less stable. Okay. What about trans isomer? In trans isomer, either the two methyl groups should be in equatorial position or the two methyl groups should be in axial position. We know very well axial position will give axial interaction, so we should avoid that conformation. And here we took the di-equatorial conformation. Okay. In the di-equatorial conformation, 1,3 axial interaction does not occur, but we have butane-Gauche interaction, right? If I take this carbon as 1, this carbon as 2, this is 3 and this is 4, right? So this is 1, 2, 3, 4 will give you a butane-Gauche interaction. So one butane-Gauche interaction exists in the trans isomer, but compared to cis isomer, in trans isomer we have only one butane-Gauche interaction. Therefore, trans isomer is more stable over cis isomer in 1, 2 dimethyl cyclobutane. Are you clear? Then here I will take another example. It is actually 1, 3 dimethyl cyclobutane. In 1, 3 dimethyl cyclobutane, the cis isomer, where the two methyl groups present in axial position, then the trans isomer in which one methyl group in axial, the other methyl group in equatorial, and another cis where both methyl group are in equatorial. So we have three possible extreme conformations. Now in this conformation, since the two methyl groups are occupying axial position, there will be 1,3 diaxial interaction is there, and this diaxial interaction is strong interaction, so it raises the potential energy of the molecule. Apart from this, there will be two butane-Gauche interactions, right? What are the butane-Gauche interaction? If I take this carbon as 1, 1, 2, 3, 4, this is one butane-Gauche interaction, and if I take this carbon as 1, 1, 2, 3, 4, this will give another butane-Gauche interaction. So this molecule also has two butane-Gauche interaction. Therefore, this conformation is highly unstable compared to other conformations. Then, in the trans conformation, one group in axial, the other group in equatorial. So equatorial group does not show any axial interaction, whereas this axial group will show axial interaction, one axial. Therefore, potential energy rises slightly. And this conformation has one butane-Gauche interaction. See, if I take this carbon as 1, 1, 2, 3, 4, right? This is 1, 2, this is 3, and this one is 4. So here we have one butane-Gauche interaction. This butane-Gauche interaction will raise the potential energy slightly. Okay, but compared to this conformation, this is more stable. In the cis isomer, this is conformation with the two alkyl group in di-equatorial form. In di-equatorial form, there is no axial interactions, and there is no butane-Gauss interactions also. Therefore, this conformation is the most stable conformation among the three. Okay. So, in 1,3 dimethyl cyclobutane, right, diequatorial cis conformer is the most stable conformer. Are you clear? Then, this is an important question here. In this question, I like to give some information. That's why I have taken this question. So, draw the stable conformer of trans 1-methyl 3-ethyl cyclobutane. Okay. So, here I have shown this in a planar form. So, in the planar structure, if I take this as carbon 1, this is 2, and this carbon is number 3. So, in carbon 1 we have methyl, and in carbon 3 we have ethyl group. Okay, Me represent methyl, Et represent ethyl here. Okay, since it is a trans isomer, so if one group is projected towards you, the other group should be behind the plane, right? Note that in 1,3 disubstituted compound, trans means one group should be axial, the other group should be equatorial. I have given this information in the last slide, in the 2 slides before. So, just go through this is very important. Okay. So, one group should be axial, the other group should be equatorial. So, if it is so, I can place methyl group in axial and ethyl group in equatorial. This is one possible conformation. And the other possible conformation is place ethyl group in axial and methyl group in equatorial. This is another possible conformation. But among the two, which is more stable? Since this group in axial, there will be 1,3 axial interaction exists between methyl group and hydrogen, and here we have 1,3 axial interaction between ethyl group and hydrogen. Since the size of this group is larger, okay, this interaction, ethyl hydrogen steric interaction is more compared to the methyl hydrogen steric interaction. Okay, and this interaction provides more potential energy to the molecule. So, energy of the molecule increases, stability decreases. Therefore, among the two conformation, this conformation is more stable over this. Okay, are you able to follow? Yeah, this is very, very important information. Keep this in mind. So, whenever two different groups exist in the molecule, right, the larger group prefer to occupy equatorial position. Yes. Yeah, so this is regarding cyclobutane. Now we'll start cyclopentane molecule. Cyclopentane in planar form, the point group of the molecule is D5H. In planar form, there are 5 hydrogen above the plane and 5 hydrogen below the plane. So there are 10 pairs of eclipsed interaction between hydrogen exist. So this is one eclipsed interaction. Like this, we have 10 pairs of eclipsed interactions. Each pair will give you 1 kilocalorie, will raise the potential energy by 1 kilocalorie per mole. So 10 means 10 kilocalorie per mole of energy, okay, increases due to this interaction. 10 kilocalorie per mole. Kilocalorie per mole. 10 kilocalorie per mole of energy increases. But when the cyclopentane takes the non-planar Puckett ring form, okay, so this is the Puckett ring form where 4 carbon atoms are in one plane and 1 carbon atom is not in the plane. It may be above the plane or below the plane. Because of this, what happens? The eclipsed interaction between hydrogen decreases. Is it correct? Because if all carbon atoms are planar, then more eclipsed interaction will be there. But now only 4 carbon atoms are in one plane and 1 carbon atom is not in the plane. Therefore, eclipsed interaction decreases. Okay, but this cyclopentane undergo pseudo rotation. What is meant by pseudo rotation? See, this carbon is above the plane, right? So in the gas phase, this carbon will go down and become planar. Once this becomes planar, the adjacent carbon, okay, it may go up. It may go up. and that carbon will come down, then this may go up. Like this, the skeletal movement will be there, also called skeletal vibration. This skeletal vibration is sometimes called as pseudo rotation. This pseudo rotation will provide some potential energy to the molecule, roughly 17 kilojoule per mole, or we can say 1.4 kilocalorie per mole. This 1.4 kilocalorie per mole, right, makes this Foucault ring form, makes this Foucault ring form slightly unstable. But if you compare the planar form and the Foucault ring form, right, even though the energy difference is less, but Foucault ring form is more stable over the planar form. Okay, and this Foucault ring form of cyclopentane belongs to the point group CS, and this shape is called as open envelope shape. Okay, this shape is open envelope shape. Then remember, this is very important, cyclopentane in gas phase undergoes pseudo rotation. Pseudo rotation is sometimes called as skeletal vibration. Are you able to follow? And this pseudo rotation provides some potential energy to the molecule. So 17 kilojoule per mole of energy is introduced because of the skeletal vibration, right, or pseudo rotation. Then in the open envelope shape, right, the 4 carbon atoms are in one plane and 1 carbon is above the plane, and in the open envelope conformation there are 3 axial hydrogens and 3 equatorial hydrogens. Okay, the hydrogen present in these 2 carbon are neither axial neither equatorial. Okay, they are neither axial nor equatorial, so you need not worry about these hydrogens. Able to follow? And we have 3 axial hydrogen. This is one axial hydrogen, this is one axial, this is another axial, and this one is another axial. So there are 3 axial hydrogen and 3 equatorial hydrogens exist in the cyclopentane molecule. Are you able to follow? Okay. Yeah. Today I stop here. We'll continue this in the next lecture. In the next lecture, I'll show some examples for cyclopentane. After that, we'll start cyclohexane. Okay. I stop here. Thank you.